This is Algebra 2 a trig 3a.2a. We're going to graph rational functions. A rational function has the form of p of x over q of x. That could be any polynomial on top divided by any polynomial on bottom. Well, we're going to do it a little bit more basic than that. The inverse variation that we've been working with has looked like a over x, where a is your constant. So we're not having an x value in the numerator. That's what makes these simple rational functions. So we're going to talk about graphing. The parent function, the most basic one that we can come up with, is when the a value is 1. That is a rational function. Which consists of two symmetrical halves called branches. So the symmetrical part is actually pretty important. That's going to help us with graphing. We don't have to do as much calculation. As soon as you calculate one side, you can figure out the other side, because they are symmetrical. Notice that as x gets smaller here, the y value is getting closer and closer to the x-axis. Think about what that means. When you say 1 divided by negative 1, we get the value of negative 1. When you say 1 divided by negative 2, we get the value of negative 1/2. And 1 divided by negative 5, 1, 2, 3, 4, 5, we get the value of negative 0.2. No matter how far out we go, negative 20, we're going to be way out here. We're never going to touch 0. 1 divided by negative 100, we're never going to touch the x-axis. We're just going to get closer and closer and closer to it. Now, what happens when x gets bigger and bigger? What happens when we say 1 divided by negative 1/2? What if we're only at the halfway location? We're going to be at negative 2. 1 divided by negative 1/8. Just 1/8 is going to be way down here at 8. Negative 8. Okay, so the smaller it gets, the closer you're going to get to that. And if you go just a teeny bit, you're going to be way down there. If you barely go over at all, 1/100th, you're going to be way down low. Okay, that's what that's saying. So you're never going to touch the y-axis. You can't touch it. So we call this an asymptote. We draw that with a dashed line. X equals 0. And you noticed that we never touched 0. So we have our asymptote of y equals 0. Okay, that is your horizontal asymptote and your vertical asymptote. Vertical goes up and down. Horizontal goes right and left. So our domain, you can have any x values except 0. So it's non-zero real numbers. All non-zero real numbers. Same thing for the range. any function in the form of y equals a over x has the same asymptotes. As long as that's a constant number up there, we're going to have the same asymptotes. As long as we're not translating. We'll translate, which will change that. But if we're in this format, we have the same asymptotes. So let's try. Notice what we're trying to graph. Y equals 4 over x. So that's in that same format of 1 over x. It's a constant number over x. So I know that we're going to have a branch down here and a branch in the first quadrant. Third and first quadrant is what I'm expecting, because a 4 is a positive number, just like it was here when a was a positive number. What's my vertical asymptote? What am I not going to touch? X equals 0. That's my vertical asymptote. I can't get an answer. It's shaded in. So now I'm going to pick numbers to the left. You can pick any numbers you want to the left of your vertical asymptote. Doesn't matter. I would suggest picking numbers that went well with 4. So what number goes into 4 pretty well? Well, 1 goes into 4 pretty well. 2 goes into 4 pretty well. 3 doesn't go into 4 very well. What's another one? 4. 4 goes into 4 pretty well. So I'm going to try -1, -2, and -4. -1 would give me what? So when x is -4, when x is -1, I get -4. When x is -2, I get -2. When x is -4, I get -1. So you need to show your dots. Not just a curve, just not a branch. I need to see where that branch was supposed to go through. Be specific. Now, because this is symmetrical, I could come over here and calculate it again, which is totally fine. But notice, if these are supposed to be symmetrical and this is my origin, I went 1 to the left and down 1, 2, 3, 4. So I'm going to go 1 to the right and up. 1, 2, 3, 4. I went 2 to the left and 2 down. So I'm going to go 2 to the right and 2 up. 4 to the left and 1 down. 4 to the right and up 1. So I know where those dots are supposed to be. I don't have to recalculate them all. I took a little bit of time to calculate the first set. I didn't use my calculator. I know that the numbers 1, 2, and 4 work well with 4. 1 divided by, or actually 4 divided by 1 is 4. That's what we got. 2 divided by 4 is 2. That's what we got. 4 divided by 4 is 1, and that's what we got. So if you get stressed out with the calculations, you only have to do half the calculations. We have a horizontal asymptote here at y equals 0. And a horizontal asymptote at x equals 0. The graph is never going to get below that. vertical asymptote was y equals 0. Oh, vertical, that's up and down, I'm sorry. That was x equals 0. The horizontal asymptote is y equals 0. What's my domain? What x values could we possibly have typed in here, done a calculation with? Yeah, all real numbers except x equals 0. What answers could we get? What y values? What's the range? Looking at all these y answers, got negative ones, got positive answers. What's the one value you can't get? You can't get 0. So I can get any number. So all real numbers. Except y equals 0. Okay, let's take a look at comparing these two. Notice that I went over 1 and up 1. That was with this graph. But in this case, I'm going over 1 and up 4. So what happened with this graph compared to this one? Are they exactly the same? This is over 1 up 1. This is over 1 up 4. So this one had a vertical stretch by a factor of 4. So 1 times 4 brought me up here. At 2, I'm at a half. At 2, I'm at 2. So you do a half 4 times, and I'm up at 2. So I stretched it by a factor of 4. So the comparison is a vertical stretch by a factor of 4. Now, what do we notice that is different about this equation compared to our regular format like that? What do we see that's different? Pretty obvious. Okay, we have our h and k. And what do h's and k, what have they done to us in the past? It translates the graph. If we think about a parabola, we think about how the vertex is moved. Well, these are called hyperbola, and they don't have actually a vertex, but it does get translated. So our asymptote is going to be translated h units. So if it says minus h, it's actually a positive h value. So it's going to be moved h units. And the horizontal asymptote is going to be y equals k. So those are your new asymptotes. We're going to plot 3 points to the left and 3 points to the right of the vertical asymptote, just like we did before. And we're going to draw the 2 branches. And that makes a hyperbola. And we're going to plot the points and approach the asymptotes. So we come down here. If we're thinking about what the parent function would be, we could call it 3 over x. That would be kind of your parent function. 1 over x, that would have a vertical stretch of 3. It would be reflected over the x-axis. But typically, we would consider that our parent function. But I could see the argument of 1 over a as being the best parent function. Anyway, what we're going to do is look for our asymptotes. I see that this is x minus 1. So I'm going to have a vertical asymptote where x equals positive 1. Because positive 1 is what makes this 0. 1 minus 1 is 0. We can't have 0 down here. That's what makes it an asymptote. We're going to have a horizontal asymptote at the k value, at 2. So that's y equals 2. Because this is negative, I'm expecting the branches to be in the opposite quadrants. Before, on the other page, we had our 2 branches in the first and third quadrant. Now with a negative, we're going to reflect it over the x-axis, and that's going to give us in the second and fourth quadrant. That's because of the negative. Our vertical asymptote for our graph is going to be 1. Then we want to pick values to the left and values to the right. This gets a little bit more complicated in terms of trying to figure out what values would work best. If you're good with the numbers and you can think a number minus a value would work well, that would be okay. Or you can just pick values and deal with the fractions. No big deal. You can calculate it. We'll show you how to do it by hand. We don't need a calculator here. So you can pick any numbers to the left. Some people would pick 0, -1, -2. Okay, that would work. I like to spread it out a little bit more. 0, -2, -4. Spread it out as much as you can. And then we want to be symmetrical going to the right. We went 1 to the left, so I want to go 1 to the right. I went 3 to the left, so I want to go 3 to the right. I went 5 to the left, so I want to go 5 to the right. Keep it symmetrical. So now we'll do our calculations. What happens when we put a 0 in here? When x equals 0, I get -3, 0 minus 1, plus 2. That's 3 over 1 plus 2. What's that value? 5. So at 0, I'm going to be up at 5. That's not surprising. We're supposed to be in that quadrant, right? When x equals -2, we get -3, -2 minus 1. That's -3 minus 3. What's that value? That's 1 plus 2 more. That's a total of 3. So at negative 2, I'm going to be up 3. So my graph is coming down and approaching at that location. So when x is negative 4, I have negative 3 over negative 4 minus 1. That's negative 3 over negative 5. That's just 3/5. Okay, now this gets complicated. That's 3/5 plus 2. I need common denominators. What's the common denominator with 2? Well, I know my value of 2 has to have the common denominator of 5. So what's my numerator going to be? 10. So that's 13 over 5. 13 over 5. That goes in there 2 3/5. 1, 2, 3, 4. Up 2 3/5. That's just over a half. It's about 0.6. There's our graph. Now, that was a lot of calculations. We don't have to recalculate all of them. We can just count. Use this as your new origin. 1 to the left, up 1, 2, 3. So now I'm going to go 1 to the right, 1, 2, 3. What's my y value? Negative 1. So when x is 2, I'm at negative 1. Now from our new origin, 1, 2, 3 to the left, up 1. So I'm going to go 1, 2, 3 to the left, down 1. So when x is 4, my y value is 1. Now this is a little bit more complicated. What did we say we were? We were 3/5 away. We were 3/5 away from our axes. Now we got to go 3/5 the other way. That might get a little complicated. Some of you might be able to realize that. We can calculate that one if we need to. Negative 3 over 6 minus 1. That is negative 3/5 plus our 10/5 gives us 7/5. So this is 7/5. 5 goes into 7 one time. So at negative 6, 1, 2, 3, 4, 5, 6, I'm going to be up 1 2/5. There it is. We made it. We graphed it out. We didn't use a calculator. We did not type that into our calculator. We did not look at the table on our calculator. What's our domain? All real numbers except x equals 1. And our range, the y values, are all real numbers except y equals 2. That's the value you can't get. So we've had from the basic graph. Okay, so maybe it's even better to say our parent function is 1 over x. That's really our parent function. It has a negative sign, so we have a reflection over the x-axis. We have a vertical stretch by 3, and we've been translated. 1 right, and 2 up. That was our transformation. R, S, and T. S is your stretch or shrink. Okay, last one. The time, which is small t, in seconds, that it takes to travel 1 kilometer can be modeled by this. This is sound. Okay? Where capital T is the temperature. How long does it take sound to travel 5 kilometers? When the temperature is 35 degrees Celsius. Well, the time that it takes at a temperature of 35 we have 1,000 divided by 0.6 times 35, then we're adding our 331. That's going to say that it's taking 2.84 seconds to travel 1 kilometer. But what's it going to be for 5 kilometers? If you times that value by 5, we'll get 4.2 seconds to travel 5 kilometers. You too.